My sincere greeting to one and all. I am Tamanna from Basic Chemistry Honors Second Year. Today I am here with chapter Chemistry of Lanthanide Elements. This is our chapter from Inorganic. Let's start. We have learned that elements in which the last electron enters in f orbital of their atom are called f block elements. In these elements, the last electron is added to the outermost called antipenultimate energy level, example n-2f. These elements are called inner transition elements because these constitute transition series with transition series d block elements. They consist of two series of elements placed at the bottom of the periodic table. These two series are formed by filling of electrons in 4f and 5f orbitals and are called lanthanides and actinides respectively. The series involving the filling of 4f orbital following lanthanum La atomic number 57 is called lanthanides series. The elements present in the series are called lanthanides. There are 14 elements in this series, starting with cerium atomic number 58 and ending with lutetium Lu atomic number 71. The name lanthanide is derived from lanthanium, the first member of the series. These lanthanides are also sometimes referred to as lanthanons. All these elements have closely similar properties and therefore are considered together. The reason for the similar properties is that the 4f orbital which the electrons are added are embedded in the inner shell within, while 5d and 6s electrons have similar configuration are exposed more to the surrounding. Because to their similar properties, their separation and identification proved to be very difficult task. The first stage in the separation was to get them as oxides. However, the occurrence of the oxides of lanthanides was very rare. Therefore, these elements have also been called rare earth element. Nowadays, the term rare earth is not used. The sustainable deposit occurs in Sandev, USA, USSR, and India. Journal characteristics of lanthanides. The important journal characteristics of lanthanide are discussed below. First, electronic structure and position in the periodic table. The lanthanides involve the gradual filling of 4f orbital. It may be noted that the energy of the d orbital 5d and the next inner shell f orbital 4f are closely similar, and therefore the order of filling the 4f orbital in the atom show quite irregularities. And lanthanum 5 atomic number 57, both 5d and 4f orbital become stable due to increased effective nuclear charge as a result of the poor shielding effect of 6s electron. Therefore, it is observed that at lanthanum, the incoming electron enters the 5d orbital and its electronic configuration is lanthanum atomic number 57, its electronic xenon 5d1 6s2. However, as we move further after lanthanum 2, energy of 4f subshell become lower than the 5d subshell, and therefore the next electron in cerium enters the 4f subshell. The electronic configuration of cerium is cerium atomic number 58 is xenonium 4f2 5d0 6s2. The filling of 4f orbital continues until we reach deuterium, in which the 4f subshell get completely filled. Electronic configuration of deuterium atomic number 70 is xenon 4f14 6s2. Now, after 6s and 4f subshell have been filled, the next electron goes to 5d subshell. The configuration of lutetium Lu is lutetium atomic number 71 is xenon 4f14 5d1 6s2. These constitute lanthanides. The general electronic configuration of lanthanides may be written as xenon 4f0 to 14, 5d0 to 1, and 6x2. The electronic configuration of lanthanides are given in table 1. Physical properties. The important physical constant of lanthanides are given in table 2. These are discussed below. First, ionization energy. The lanthanide have fairly low ionization energy. In general, the first and second ionization energy of lanthanide increases. The increase in atomic number, but the variation is small and irregular. The variation of ionization energy with atomic number is shown in figure 1. It is clear from the figure that some derivations are observed in the regular increasing order such as EU, GD, UV, LU. These are attributed to the stability of half-filled and completely filled F subshell. The first ionization energy are of the order of 560 kilojoule per mole inverse, and second ionization energy are of the order of 1150 kilojoule per mole inverse. Uh, these values are quite comparable to alkaline earth metal, especially calcium, whose first ionization energy is 589 kilojoule per mole and second ionization energy is 1145 kilojoule per mole. Second, melting and boiling point. Lanthanides have fairly high melting and boiling point. However, the melting and boiling point do not show any regular trend as we move from lanthanide to lutetium in the series. Inspection of table 4.2 shows that europium and ytterbium have unacceptably low melting and boiling point. These atoms from EU2 positive to YB2 positive ions are and result in weaker metallic bonding because are less than 3 electrons per atom in the metallic bond. The other lanthanide atom give 3 electrons per atom in the metallic bond. Therefore, melting and boiling point of EU and YB are low as compared to value of other lanthanide element. Density. The densities of lanthanides are low, which ranges from between 6.7 to 9.74 gram centimeter inverse cube. However, there is no definite trend in the density value of lanthanides. With increase in atomic number, uranium and deuterium have unaccepted low values. Fourth, heat of fission and heat of vaporization. The heat of fission and heat of vaporization also do not show definite trend with increase in atomic number. Fourth, electronegativity value. The electronegativity value of lanthanides between 1 to 1.15 are quite close to those of alkaline earth metals S block elements. Therefore, lanthanides are accepted to form ionic compound. Sixth, electropositive character. Because of low ionization energy and electronegativity value, the lanthanides are electropositive like S block element. Third, oxidation state. The common oxidation state of all the lanthanides is +3. In addition, some lanthanides show +2 and +4 oxidation state also. These are some by those elements which is by doing so attain the stable F0, F7 and F14 configuration. For example, first cesium and Tb exhibit +4 oxidation state. Cerium and terbium attain 40 and F0 and F7 configuration respectively when they go to +4 oxidation state as shown below. Second, europium and ytterbium exhibit +2 oxidation state because they get F7 and F14 configuration in +2 oxidation state as shown below. La, Gd and Lu exhibit only +3 oxidation state. These elements show +3 oxidation state only because by losing 3 electrons they acquire stable configuration of empty, half-filled and completely filled 4f subshell respectively. as shown below. Exp- uh, Exceptional examples. Some other elements show +2 and +4 oxidation state even though they have electronic configuration other than F0, F7 or F14. For example, Sm and Tm show +2 state having F6 and F13 electrons respectively, in which they have one electron less than half filled or completely filled configuration. Similarly, Br, Nd and Dy show +4 oxidation state having F1, F2 and F8 electronic configuration. The stability of these unusual oxidation state may be dependent upon some other thermodynamic and kinetic factors which are of significant importance, and but these are less stable than the +3 state, which is characteristic of this family. The outer electronic configuration of lanthanide is different oxidation state are given in table 3. Fourth, color and spectral properties. The lanthanides are silvery white, but many lanthanide ions are colored both in the solid state and in the aqueous solution. The colors remain same even on the change of anions. Therefore, the colors are characteristic of the lanthanide ion. The color of the ion depends upon the number of unpaired electrons, because it has been observed that the ion containing NF electrons have almost similar color to those of 14 NF electrons. The different ion having NF and 14 NF are their color are given in table 4. However, it has been observed that some di and tetra positive ions having same number of isoelectronic ions are, as tri-positive ions do not have same color. For example, Sm2 positive and Eu3 positive have same number of unpaired electrons, but they have different colors. So other examples are given in table 5. The color of lanthanide ion arises due to the absorption of light from the visible region of the spectrum, resulting in the electronic transition within the 4f level FF transition. A remarkable characteristic of the spectra of the tripositive lanthanide ion is that the absorption bands are extremely sharp line-like band in ultraviolet, visible or near infrared region. Many of these bands are line-like and become even narrower as the temperature is lowered. This behavior is in contrast to absorption band of DD transition, which have broad absorption band. The band of lanthanide ion are so sharp that they are usually useful for characterizing the lanthanide ion. The main reason for very sharp absorption band is that the 4f orbital lie deep in the atoms of these elements. Therefore, they are effectively shielded from the surrounding by the overlaying 5f and 4p orbital, and consequently, the absorption band arises mainly from the electronic transition within the 4f level. Thus, the absorption band shows a little dependence on the nature of the ligand. In addition to FF transition, sometimes color of lanthanide ion is also attributed to FD transition. The FF absorption transition of lanthanide ion have low intensity because they do not allow, whereas F to D transition are allowed. In contrast to FF transitions, the FD transition are allowed and hence show very intensive absorption band. For example, the F to D transition observed in cerium 3 positive and tritium 3 positive are very intensive. Magnetic properties. All the lanthanide ions, with the exception of Al3 positive, Lu2 3 positive, Ce4 positive and Yb2 positive ions are paramagnetic because they contain unpaired electrons in their 4f subshell. The ions La3 positive, Lu3 positive, Ce4 positive and Ub2 positive have which have 4f0 and 4f14 electronic configuration are diamagnetic because they have no unpaired electrons. The magnetic property of lanthanide are different from those of the transition elements. As we know that the magnetic moment arises from two types of motions of the electron. The spin motion of electron around its own axis produces magnetic moment called spin magnetic moment, while the orbital motion of the electron around the nucleus produces magnetic moment called orbital magnetic moment. The spin motion of electron around its own axis produces magnetic moment called spin magnetic moment, while the orbital motion of electron around the nucleus produces magnetic moment called orbital magnetic moment. The observed magnetic moment of the substance is due to the contribution of both the spin momentum and the orbital momentum. In the case of transition elements, d block elements, the magnetic moment mainly corresponds to the spin-only magnetic moment. This is due to the fact that the d orbitals are not well shielded from the environment and take part in bond formation with ligand, atom, ion, and molecules. As a result, the d element electrons of the metal interact strongly with the ligand surrounding the metal ion. Due to the electric field of the ligand, the orbital motion of the electron get restricted and thereby the orbital momentum of these electrons get changed. The magnetic moment of d block elements thus arises mainly for the contribution of spin motion of the electron only. The spin only magnetic moment is given by mu spin only gives under the root n into n plus 2, where n is the number of unpaired electrons. This relationship gives almost correct values of magnetic moment for d block elements. However, the above relationship is not valid in case of d block element. In this element, the 4f orbitals are well shielded from the surrounding by the overlaying 5f and 4p subshells. As a result, the electric field of the ligand surrounding the metal ion does not restrict the orbital motion in the electron. Thus, orbital contribution is not gauged. Therefore, the magnetic moment of lanthanide ion is due to both electron spin and orbital motion of the electron. This may be calculated from the relation mu is equal to under the root s into s plus 1 plus l into l plus 1, where s is the resultant spin quantum number and l is the resultant orbital momentum quantum number. The theoretical and experimental observed magnetic moment value of are given in table 6. The magnetic moment of lanthanide depend upon the atomic number and the number of the unpaired electrons. For the ion La 3 positive F0, Gd 3 positive F7 and Lu 3 positive F14, the magnetic moment corresponded to the spin only value. For these configuration, they have no orbital angular momentum. L is equal to d0. The above expression become mu is equal to under the root 4s into s plus 1. The magnetic moment may be calculated only on the basis of the spin only value. Here s is equal to ns and where n is the number of unpaired electrons and small s is the spin quantum number. 1 by 2 for 4f0 La3 positive and 4f14 Lu2 3 positive configuration, there is no unpaired electron and n is 0 and their magnetic moment is also 0, diamagnetic. For 4f7 configuration Gd3 positive, the magnetic moment can be calculated on the basis of spin only value because orbital angular momentum is 0. L is equal to 0 as Gd3 is equal to xenon for f7, number of unpaired electrons, n is equal to 7, s is equal to half, small s is equal to 7 into half is equal to 7 by 2, mu is equal to under the root 4s into s plus 1 is equal to s is 4 into 7 by 2 under into 7 by 2 plus 1 under root 63 is equal to 7.9 Bohr magneton. This can be calculated as mu is equal to under root n into n plus 2, where n is the number of unpaired electrons. 7 under the root all over 7 into 7 plus 2 is equal to under root 63 is equal to 7.9 Bohr magneton. The magnetic moment of tripositive lanthanide ion are plotted in figure 2. La3 positive and Lu3 positive are diamagnetic, no unpaired electron. It is observed that the value increases up to nillidium and then decreases to 1.47 for Sm3 positive ion. It increases again and reaches a maximum value for dysprosium and holmium. Thereafter, it starts decreasing and becomes 0 for lutetium, which is diamagnetic. The magnetic momentum of lanthanide ion at 27 degrees Celsius, the only spin value are shown as dotted lines, while spin and orbital motion value are shown in solid line. The unusual shape of the curve arises because when the F subshell is lesser than half full, the spin and orbital magnetic moment work in opposite, but when the F subshell is more than half full, they work together. Sixth, ionic radii lanthanide contraction. We know that as we move down a group, atomic size, covalent or ionic radii normally increases. This is mainly due to the additional shell or electron between the successive period. However, as we move across a period from left to right, atomic size decreases. This is attributed to the increasing effective nuclear charge, as a result of which the outermost shell of electrons is attracted more and more. Consequently, the size decreases. For example, the covalent radii of alkali metal increases from lithium 1.23 angstrom to cesium 2.35 angstrom, and for halogen from F fluorine 0.72 angstrom to iodine 1.33 angstrom. If we consider the ionic radii of lanthanide, we get very interesting observations. For comparison sake, we take the ionic radii of trivalent ions M3 positive, which are most stable. These are shown in figure 3. It is clear that ionic radii decreases from one element to another in the lanthanide series, but decrease is very small. It has been observed that from cesium-3 positive to atomic number 58 to lutetium-3 positive atomic number 71, the ionic radii decreases from 1.03 angstrom to 0.86 angstrom. Obviously, for an increase of atomic number 14, the decrease in ionic radii is only 0.17 angstrom. This is very small decrease in comparison to elements of other group and period. Similarly, on moving from cesium to lutetium, the atomic radii also decreases from 1.65 angstrom to 1.56 angstrom, and the decrease is only of 0.09 angstrom. This is a small steady decrease in ionic and atomic size of the lanthanide element, with the increase in atomic number is called lanthanide contraction. Ionic radii of tripositive lanthanide. Cause of lanthanide contraction. In lanthanide series, the 4f electrons are being added on one at each step. As we move from one element to another, the shielding of one f electron by another from the nuclear attraction is quite weaker than due to the shape of the f orbital. The nuclear charge, however, increases by 1 to each step. Hence, the increasing atomic number and nuclear charge, the effective nuclear charge experienced by the shielding of one f electron by another from the nuclear attraction is quite weak due to the shape of 4f orbital. The nuclear charge, however, increases by 1 to each step. Hence, with increasing atomic number, the nuclear charge, the effective nuclear charge experienced by each 4f electron increases. Hence, the inward pull experienced by the 4f electron increases, and this causes a reduction in the size of atom or ions. The sum of successive reduction give the total lanthanide contraction. Consequences of lanthanide contraction. Lanthanide contraction have very significant effect on the relative properties of the element which precede and which follow the lanthanide in the following periodic table. Some important consequences of lanthanide contractions are given below. First, steady decrease in size. There is a regular decrease in the ionic radii of lanthanide. Second, electronegativity. There is slight regular increase in the electronegativity of the trivalent ion. Third, electrode potential E naught value. There is a small but smooth increase in standard electrode potential value E naught for the process from lutetium 2.56 volt to minus 2.25 volt for lutetium. Fourth, resemblance to the second and third transition series. The lanthanide contractions affect the chemistry of second and third transition series. As we see from table 8, there is a regular increase in size from secondium to uranium to lanthanum. Similarly, we accept normal increase in size in the other groups. However, after lanthanide, the increase of ionic radii for second and third transition series almost vanishes. The pair of element ZR, HF, NBTA, MOW, etc. possess almost same size. The property of these elements is also very similar. Lanthanide compounds. The lanthanide are soft and silvery white. They are electropositive and therefore they are reactive. They are reactive. They react with hydrogen, forming the hydride of composition LnH2 and LnH3. These also react with several other non-metals including oxygen, halogen, sulfur, nitrogen, phosphorus, carbon, silicon, etc. Most of the lanthanide compounds are known as +3 oxidation state. However, some compound of lanthanides in +2 and +4 oxidation state are also known. The important lanthanide compound are discussed below. Compound in +3 oxidation state. This is the most common oxidation state of lanthanide oxides. All the lanthanide tarnish readily in air. These burn with oxygen, forming the oxide Ln2O3. These are also obtained by the ignition of hydroxide, carbonate, nitrates, etc. Ln2O3 are well characterized. Lanthanide oxide absorb water and carbon dioxide from the air to form the hydroxide and carbonate respectively. Therefore, the lanthanide oxides Ln2O3 are strongly basic and their basic character decreases as atomic number increases. For example, La2O3 is strongly basic while Lu2O3 is least basic. The lighter or more basic oxide resembles the oxide of group second element, alkaline earth metals. All are soluble in water but observe it from hydroxide. They dissolve readily in aqueous acid to form solutions which contain the LnH2OX3 positive ion provided they are kept on the acid side of pH 5 to prevent hydrolysis. Hydrous hydroxide can be precipitated out from these solutions by the addition of ammonia and aqueous alkali. Ln2O3 adopt three types of structures. A type. These consist of LnO7 unit which have approximate to capped octahedral geometry. They are favored by the highest lanthanides. B type. They consist of LnO7 unit which have capped trigonal prism and capped octahedral geometry. They are favored by middle lanthanide. C type. They have fluoride structures in which 1/4 of an ion are removed in such a way so as to reduce the metal compound coordination number from 8 to 6. These are favored by middle and heavy lanthanide. Hydroxide. The lanthanide reacts slowly with cold water, but more readily rapidly on boiling with the liberation of hydrogen and form the corresponding lanthanide hydroxide. 2 Ln plus 6 mol of H2O gives 2 LnOH3 plus 3H2. The hydroxide can also be prepared by adding dilute solution of sodium hydroxide to a solution containing lanthanide plus 3 ion. The hydroxides are precipitated as gelatinous precipitates. They are ionic compound and are basic. Lanthanide hydroxide are less basic than CaOH2 but more basic than AlOH3, which is amphoteric. The basic character of lanthanide hydroxide decreases with the increase in atomic number along the series. Therefore, LaOH3 is more basic while LuOH3 is least basic. This is due to the lanthanide contraction. Crystalline LnOH3 have a 9-coordinated tri-capped trigonal prismatic structure. Uh, Chalcogenides are of similar chemistry to the oxide are known for lanthanides. In general, these are stable in dry air but they are hydrolyzed in the presence of moisture. If heated in air, they oxidize, especially sulfides, to basic salt of the corresponding oxyanion and show varying susceptibility to attack by the acid with the evolution of H2Z. Trivalent chalcogenides Ln2Zn3 have been obtained by a variety of methods such as direct combination, acid action of H2S on the chloride or oxide. In case of sulfides, when Ln2Z3 are heated with an excess of chalcogen in sealed tube at 600 degrees Celsius, product with composition up to or nearing LnZ2 are obtained. These are polychalcogenides with the metal in +3 oxidation state. Halides. Lanthanides in oxidation state 3 form trihalides. Anhydrous lanthanide 3 fluoride are prepared by adding HF or NaF solution to the salt solution containing Ln3 positive ion. The fluorides are very insoluble and therefore are easily precipitated from their solution by HF and NF. However, with excess F negative, the fluorides of heavier lanthanides smaller size may form soluble complex LnFH2O and 2 positive. Anhydrous lanthanide chloride are prepared by heating the metal in the atmosphere of dry chlorine and or by heating lanthanide oxide by carbonyl chloride, etc. As the chlorine are dilute non-volatile solid. These are soluble in water and crystallizes with 6 or 7 molecules of water of crystallization. It may be noted that simple anhydrous lanthanide halide cannot be prepared by simple heating the hydrate salts as they form lanthanide oxochloride LnOCl instead of dehydrating the anhydrous halides. Anhydrous halide can also be prepared by heating the oxides with appropriate ammonium halides. The aqueous solution of the other trihalide are prepared by dissolving the oxide of or carbonates in aqueous HX and hydrated having 6 to 8 H2O moles can be crystallized. Anhydrous trihalide fluoride or chloride can be prepared by terminal dehydration of these hydrates of lighter lanthanide. The bromide ion or more sustainable to hydrolysis. The dehydration leads to the contamination of oxohalides. Therefore, these are preferably prepared by direct combination. 2 Ln plus 3x2 gives 2 Ln x3, where x is bromine or iodine, and anhydrous trihalide or ionic high melting crystalline substance. However, trifluorides are extremely dilucent. Nitrides at high temperature, the lanthanide react with nitrogen to give nitride for the formula LaN. It gets hydrolyzed by water like aluminium nitride AlN to give the corresponding hydroxide with the liberation of ammonia. Oxosalt of lanthanide. A large number of oxosalts of lanthanides are known. They include carbonates, nitrides, sulfides, oxalates, phosphates, and perchlorates. They are generally prepared by dissolving the lanthanide hydroxide or carbonate in the corresponding acid. For example, given below. The resulting solution are cooled when crystals of hydrated oxo salts are obtained. Double salt of lanthanides. Lanthanide sulfate are known to form double salt with ammonia and alkali metal sulfite. Some common examples are given below. It may be noted that the double salt in case of alum are generally associated with many as 24 water molecules of crystallization. However, the double salt of lanthanide cannot be associated with as many as 24 water molecules of crystallization. This is because the lanthanide ions are too large to coordinate with 24 moles of water molecules of crystallization octahedrally as in compounds in plus 4 oxidation state. Among the lanthanide, only cerium, paraxedium, and neodymium, tribinium, and disulfurium show plus 4 oxidation state. The only lanthanide which exists in plus 4 oxidation state in solution and has any aqueous chemistry is cerium plus 4, and cerium plus 4 solution are extensively used as a versatile oxidizing agent in volumetric analysis. Aqueous cerium plus 4 solution can be prepared by oxidation of cerium 3 plus solution with a strong oxidizing agent such as ammonia pre-oxidized sulfide NH4 twice S2O8 cerium 4 solution are also used in inorganic reactions for the oxidation of alcohols, aldehyde, ketone, etc. The common compound in plus 4 oxidation state of cerium are cerium O2 white when pure and CEO2 into H2O a yellow gelatinous precipitate. CEO2 can be obtained by heating the metal with or CeOH3 or C2O4 thrice in air. CEO2 is insoluble in acids and alkalis but dissolve when reduced, giving C3 positive solution. The analogous dark color PrO2 and TbO2 are obtained from their stable oxides Pr6O11 and the major difference between the dihalides of uranium and calcium is that the dihalides EuX2 have magnetic moment of 7.9 Bohr magneton corresponding to 7 unpaired electrons, whereas calcium correspond are diamagnetic. The lanthanide plus 2 state Nd2, Pm2, Sm2 and Gd2 are only found in solid dihalides LnCl2 and LnI2. These dihalides can be conventionally prepared by reducing the corresponding trihalides when the lanthanide metal itself or by hydrogen or sodium and amalgam. The dihalides are prepared from corresponding trihalides by reduction with lanthanide metal itself. The most stable diiodides SmI2, EuI2 and YbI2 are prepared by thermal decomposition. SmI2 and YbI2 can also be prepared in quantitative yield by reacting the metal with 1,2-diiodoethane in anhydrous THF at room temperature. The stable diiodate of samarium, europium and deuterium can be prepared by the thermal decomposition of their triiodide as, with the exception of EuX2, all the dihalides are easily oxidized and liberated H2 from water. The diiodates of cerium, Pr and Gd differ from other dihalides. They have metallic luster and very high conductivities and are reformulated as Ln3 2I negative electrons. The electron is delocalized in conduction band. Uses of lanthanides. The pure metal have no specific use and therefore these metals are extracted as a mixture of alloy. They are called mixed metals. The common use of lanthanide and their salt are given below. First, cerium constitute about 30 to 50% of the alloy of lanthanides. They are used in screening oxygen and sulfur from other metals. Second, addition of about 3% mixed metals to magnesium increase its strength and it is used in making jet engine part. Third, steel mixed with LaCePr and Nd is used in manufacturing of flame-throwing tanks. Fourth, lanthanide oxides are used for polishing glass. Neodymium and praseodymium oxides are used for making colored glasses for goggles. These are particularly useful for glass browsing as they absorb the bright yellow light. Fifth, cerium salt are used in dyeing cotton. They are also called the catalyst. Sixth, lanthanide compounds are used as catalyst for hydrogenation, dehydrogenation, oxidation, and petroleum cracking. They are also used in magnetic and electronic devices for the paramagnetic and ferromagnetic properties. 7. Gallium sulfate heptahydrate have been used to produce very low temperature. 8th, eventually, lanthanide have been used in lasers. For example, neodymium oxide dissolved in selenium dichloride chlorides have been used as a powerful liquid lasers. Ninth, cerium magnesium alloy are used in flashlight powders. Thank you.